We're living through this massive shift in how computers actually work, and it's largely driven by one chief engineer, Jensen Huang. But here's the thing. At the heart of this entire revolution, it isn't magic. It's just physics. And we're going to break it down to its first principles.
Okay, let's just start with that. We've reinvented computing. That is a huge statement, but honestly, it's not an exaggeration. We're going to unpack what that really means, getting right down to the bedrock. Look, to really get what's happening, you can't just look at the latest app or gadget. We have to reverse engineer this whole moment right down to its fundamental principles. So for the next few minutes, let's stop being observers. Let's start thinking like the chief engineer. All right, principle one. Let's start with the engine itself. The raw power, the muscle behind this whole AI explosion comes from a fundamental change in how we process information. It's all about a shift from doing things one at a time to doing everything all at once. For decades, the processor in your computer, the CPU, it worked sequentially. Think of it like a brilliant surgeon tackling one really complex task at a time, step by step. But the GPU, the graphics processing unit, it works in parallel. It's more like an army of nurses, all tackling thousands of smaller, related tasks at the exact same time. And that was the key insight. Most of the hard work in computing could be broken down and done in parallel. This visualizes it perfectly. It's from an old Mythbusters experiment. So first, they get a robot arm with a paintball gun to painstakingly paint the Mona Lisa, one single pixel at a time. Super precise, but incredibly slow. That's your CPU. Then they brought out a massive cannon that just fired all the paintballs at once, splashing the entire image into existence in a single moment. That is the GPU. It's the brute force elegance of parallel processing.
So you have this incredible parallel engine. Awesome. But the next engineering problem is a big one. How do you take all that raw power and use it to teach an AI how to interact with the real physical world?
And it's a totally fair question, right? I mean, why not just put a robot in a room and let it learn by doing, by bumping into things? Well, the answer, once again, comes down to physics. Turns out, reality is a pretty harsh and inefficient teacher. First off, gravity hurts. When a robot falls, it breaks. And repairs take time, they take money. Second, time is just slow. Learning something complex can take millions of tries, which could take years in real time. And finally, reality has no undo button. Mistakes can be dangerous and they can be permanent. So the engineering solution? You build a better reality. And this is NVIDIA's Omniverse. It's basically a digital twin of our world, and it's governed by the exact same laws of physics. Think of it like a digital gym where robots can train and fail and learn millions of times faster than they could in the real world, with zero consequences. They can literally experience a lifetime of training before their first physical bull is even tightened. And this quote just nails the point. By running all these simulations in a virtual world, you're basically hitting fast forward on time. You get to see the outcome of years of trial and error in just a few hours. So it's less of a simulation and way more of a time machine. Okay, so we've got immense power, and we have a digital world to apply it in. But there is one final universal constraint that every single engineer has to face: energy. You can't just scale this stuff infinitely if you burn way too much power doing it. And this right here is where the true engineering marvel is. Since 2016, while the performance of these AI systems has absolutely soared, the energy efficiency has improved by a factor of 10,000. That's not a small improvement, that is a complete paradigm shift. This chart really puts it all into perspective. So performance has gone up by about 6 times in that period, which, hey, that's incredible all by itself. But that is absolutely dwarfed by the 10,000x gain in energy efficiency. This is what makes it all possible. This is what makes scaling sustainable and unlocks the entire future of AI. So, what's the end result of mastering these 3 principles? What does all this engineering actually mean for us? Well, it turns out it's not about replacing humans. It's about empowering them. This quote just captures the human impact perfectly. You have a scientist who literally thought his research would outlive him, who can now actually complete it. That's the kind of power we're talking about, compressing an entire lifetime of discovery into a single career. So the most crucial takeaway is this: These principles, when you put them all together, have democratized computational power. The kind of capabilities that used to belong to a national-level supercomputer are now accessible to a single student, a single researcher, a single artist. It's a tool for amplifying human ambition. So we've literally gone from a world where we talked about a life's work to one where we can build a lifetime's work. The barriers are lower, the tools are here. So really, the only question left is the one right there on your screen.